Imagine the universe we see as foam on a vast, unseen ocean. Stars and galaxies are the foam. The deep ocean is hidden. That hidden ocean is dark matter. For years we pictured it as cold and collisionless. But what if dark matter interacts with itself? Self-interacting. Dark matter, or SIDM, says dark matter particles can bump and exchange energy. This may fix small-scale problems that CDM cannot. We see stars. We see galaxies. We see cosmic clouds of gas. Something unseen holds them together, dark matter, the ghost in the cosmic machine. CDM treats dark matter like ghosts that never touch. SIDM lets them collide just a little, where they are most crowded. Telescopes stare into galaxy hearts and find puzzles. On small scales, the standard CDM model struggles. It explains continents and oceans, but not the single grain of sand. So cosmology stands at a crossroads. About 85% of matter is dark. Maybe it is not passive. Perhaps there are dark forces and dark interactions. A hidden layer we are just beginning to glimpse. CDM particles glide through, guided only by gravity. They pile up in centers, forming sharp cusps. SIDM is more like billiard balls. In dense centers, particles collide and spread out. Cusp becomes a softer core. The needed strength is about 1 cm²/2 per gram. Tiny but important in particle physics. Collisions share energy and prevent runaway collapse. In empty space, particles rarely meet. So, on large scales, SIDM acts like CDM. It keeps the winds, the CMB and the cosmic web. It knows when to interact and when to stay aloof. This path could rewrite how galaxies grow. CDM predicts steep cusps in galaxy centers, but many dwarfs show flatter cores. SIDM collisions smooth the center to match data. CDM predicts huge numbers of satellites. We observe far fewer. SIDM can heat small halos and make gas easier to strip. Some may puff up and get torn apart. The biggest subhalos should be bright, but the brightest dwarfs are less dense than CDM predicts. SIDM lowers their central density and fits the data. One idea, 3 fixes. This consistency is why SIDM is compelling today. If dark matter interacts, it needs dark forces, not electromagnetism, or it would not be dark. One option is a dark photon. Another is a short-range Yukawa-type force. Short-range means it matters in dense centers. On large scales, predictions stay like CDM. First, simulations of CDM and SIDM. Then compare to real galaxies. Telescopes map mass, cusps versus cores. At the LHC, physicists search for dark sector particles in proton collisions. They look for unusual decays and missing energy. Underground, detectors wait for a faint nuclear recoil. Any clear signal could point to a rich, interactive dark sector. If SIDM is real, the implications are huge. It hints at a hidden universe with its own particles and forces. Dark matter stops being a placeholder and becomes a gateway. There could be dark chemistry and dark radiation. Dark forces might shape the first stars and galaxies. Maybe a very weak portal links our sector to theirs. Science advances by noticing small mismatches and asking why. CDM gave us a grand map. Anomalies point to new lands. SIDM is our ship into uncharted waters, guided by observation and theory working together. It is a journey into the unknown. What we find could change everything. We may confirm that most matter is dark and interactive, an invitation to wonder and to keep exploring. The cosmos is whispering. We are learning to listen. The adventure is just beginning. Sail with us into the dark ocean.